Today we're on our topic of significant digits and we're going to go over the rules of rounding. So let's get started. If the digit following the last digit kept is greater than 5, then increase the last digit by 1. So that's saying that if I have like 7.6 and the last digit kept is greater than 5, so that's like saying this digit here, 7, I want to keep this 7. I want to keep to the ones place. And this digit that's following the last digit kept is greater than 5. So a 6 is greater than 5. Then increase this last digit by 1, which means I round that up to an 8. That's all it's saying. And that should feel very normal for us. If the digit following the last digit kept is less than 5, then the last digit should remain as it is. So if I have a 7.4, then this last digit should be just a 7. And so that should be very normal too. If the digit following the last digit kept is 5 and has non-zero digits that follow, then increase the last digit by 1. So if I have 7.5320, something like this. In other words, I want to keep to the 7. And if the digit following the last digit kept is 5 and it has non-zero digits that follow, clearly this is greater than the 0.5. So we have to increase it by 1. We have to round this to 8. But now, if the digit following the last digit kept is exactly 5 and not followed by non-zero digits, so now it's a 7.5 and there's nothing after, or there could be zeros after, that's fine. But as long as it ends exactly in a 5, then it says, look, if it's preceded by an odd digit, then increase the last digit by 1. So since this is 7.5 exactly, then we have to look at this digit, this last digit kept. Notice that 7 is odd, so therefore we round up to 8. But the last statement here says if the digit following the last digit kept is 5, not followed by non-zero digits, so again, let's just say 6.5000. It's not followed by non-zero digits. All right, so we can follow it with 0 digits, but not with non-zero digits. And it's preceded by an even digit. Then the last digit should remain as it is. In other words, notice that this number ends exactly in 5. We want to round to the ones place. And so since it ends exactly in a 5, we look at this digit here. Notice it's 6. So therefore it's even, so we leave it alone. So we leave it as a 6. When adding or subtracting numbers, the number of decimal places is the answer to which is determined by the same number of decimal places as the measurement with the most uncertainty. That's like saying if we're taking 3.20 and we're going to add it to 1, we're just going to add 1. Notice that we have to follow the decimal point. So the decimal point would go here. We'd get a 0 and a 2 and a 4. So 4.20. Now, notice that there's only this first number has to the hundreds place or to the tens place, but they both have to the ones place. So we can't report these significant digits until they both have a position, and we have to follow that decimal point to that position. So if we were going to round, we would have to round this number to the ones place and just say the answer is 4. Namely because this number 2 is less than 5, so we round down, so it would be a 4. So this has to be to the ones place. I'll do some more examples of that in just a second. When multiplying and dividing numbers, the number of significant digits is determined from the measurement with the least number of significant digits. So if I take 15 and multiply it by, say, 10, 10 times 15, you'd say, is 150. 150. And you'd think, okay, well, 2 digits here, but there's only one significant digit here. So my answer can only have one significant digit. So then I notice that this digit is a 5, and it's followed by only zeros. So therefore the number ends exactly in a 5. Therefore I have to look at this number in front, which is a 1, and I have to round up. So that would be 200. That seems weird, doesn't it? So if I did something like maybe 3 times 5, 3 times 5, that's 15. 3 times 5 is 15. But there's only one significant digit in both of those. So my answer can only have one significant digit. So therefore I look at this number here, it ends exactly in a 5. So I have to go back to this digit. It's odd, it rounds up. 3 times 5 is 15, which is going to round up to 20. What if I had 3 times 4? 3 times 4 is 12. 3 times 4 is 12, so, okay, one significant digit, so then we'd have to round down to 10. You can think of like maybe here if I put 4 times 5. 4 times 5 is exactly 20. Notice that we have one significant digit for both. And so notice I also didn't put a decimal point here. So 4 times 5 is 20. What about 5 times 5? Well, 5 times 5 is 25. Okay, but only one significant digit. So my answer can only have one significant digit. Notice that this number ends exactly in a 5. So we have to look at the digit before the 5. Notice that now it's even. So now it's 20. So what did we learn? We learned that 3 times 5 is 20. We learned that 4 times 5 is 20. And 5 times 5 is 20. Now, according to the rules of significant digits, that's exactly correct. So it's a little different than math, so you have to really pay attention to your significant digits. So in a series of calculations, get a final result first and then round. So if you're going to multiply and add and divide and you follow all of those rules for rounding, you don't round and then round and round and round again. No, what you do is you get a final mathematical result. Get a number that is the mathematically correct. So at the end, then you round that number, okay? Now, exact numbers have infinite number of significant digits. Infinite number. So if I have a dozen eggs, I have 12 eggs. 12 is an exact number. There are an infinite number of significant digits. You might say, well, it only looks like there's 2 significant digits. Well, that's true. But it looks like that. But if we're saying a dozen is a specific amount. So exact numbers have infinite number of significant digits. Here's another example. 100 centimeters is equivalent to 1 meter. This is a definition. This only has one significant digit. This only has one significant digit. But because I'm using it as a definition, 100 centimeters are exactly in 1 meter. These are exact numbers. That means they have an infinite number of significant digits. So we have to be careful about that. So, in other words, if I have 35 centimeters and I want to know how many meters that is, Well, there's 100 centimeters in 1 meter. And so if we did that conversion, we get 0.35 meters. And then you might think, well, I'm only one significant digit up here and only one significant digit down here. And over here, there's two significant digits. So my answer can only have one significant digit. So you might just go ahead and say I have to go to this place. So then this is a 5. So then what do? I look at this number 3 and say, oh, it's odd, so I'd round up. And you might say 0.4 meters. But that would be wrong because you're assuming that there's only one significant digit here. But this is an exact number. Exact numbers have infinite number of significant digits. So these would have an infinite number of significant digits. This only has two significant digits. Therefore, my answer has to have two significant digits. And this would not be correct. Okay, the average of a data set will have the same number of decimal places that are in their sum. Well, if that's saying that if I have like 4.2 and 3.5 and 3.8, if I wanted to take the average of those numbers, so let's see, we have 4.2 plus 3.5 plus 3.8. And that gives us 11.5. And there are exactly 3 numbers here, all right? So when there are exactly 3 numbers, first of all, you might say, well, wait a minute. Hey, this should only go to one significant digit. But no. So this 3 is an exact number. And so when we take 11.5 and divide it by 3, we're going to get an answer of 3.833 repeating. So when we're trying to decide how many significant digits we have, the number 3.83, we're taking an average. So the average cannot have any more significant digits than that. It says the average of a data set will have the same number of decimal places that are in their sum. So when we look at their sum, there's only 2 spots here. There's only 2 places, 1 place past the decimal. So we have to go 1 place past the decimal. So the average is going to be 3.8 because this 3 is less than 5, so we round down. And so this is what we would do for our average. So let's look at a couple of these addition ones and subtraction ones again. So if we have 42.78 and we want to subtract 3.015, notice when we do this, we're going to have break this down. This A would be a 7, and this 10 here minus 5 would be a 5, and 7 minus 1 is a 6, and 7, and then we have a decimal point, 12 minus 3, and that gives us our 9, and then we bring our 3 down. And so this is our mathematical number. This 42.78 minus this 3.015 mathematically gives us this 39.765. But we can't report this number because notice that this number only goes to the hundredths place. This number here goes to the thousandths. So when we go to report significant digits, we cannot report it to the thousandths place. We have to report it to the hundredths place because they both have to the hundredths. So we have to report it to the hundredths place. Notice that this number ends exactly in a 5, and so therefore we have to look at this number in front, which is a 6, which is even, so we leave it alone. So the correct answer is 39.76, and that's how we do it. If we go and have something like 38.215, well, it looks kind of like a 6, doesn't it? We'll say 38.216. How's that? 38.216. And so if we want to add to that 3 let's just say we wanted to add 30 to it. Notice that we have a 0.216, we have an 8, and a 3 is a 6. So we add this number, but they do not have to the thousands, they do not have to the hundreds or to the tenths. And because there's no decimal point here, you also know that it doesn't have to the ones place. Therefore, I have to go to the tens place, which is right here. And this number is greater than 5, so it rounds up, and my answer is 70. Notice that I do not include a decimal point. 4.217, and we're going to add to that 0.003. So 7 and 3 is 10. We have a 2, we have a 2, and a 4. Now notice they all have to the thousands place. So we have to report to the thousands place. So our correct answer would be 4.220. 32.7, and we're going to add to that 0.003. So we have to the 3, we have a 0, we have a 7, and we have a 2 and a 3. So 32.7003. Well, you'd say, okay, well, they do not all have to the thousands place. That's correct. And they do not have to the hundreds place. Now this one has to the tenths place, but this 0 here, what about this 0? Well, since this number already had to the thousands place, it was already qualified. So yes, you would be able to say that you can round to this tenths place. So the correct answer would be 32.7. Okay, so these are some examples of how to round. The big thing is that if a number ends exactly in a 5, and then you look at the digit in front of it, if it's even, you round down, you leave it alone. But if it's odd, then you round up, which might seem a little weird because in most math classes, if you have 3.5, well, if you're rounding 3.5, you round that up and it would just go to 4. Well, in science class, this 3.5 would indeed round to 4, but 2.5 would only round to 2 because this digit is even. So try the homework, see how you do, and I wish you well.